In complex analysis, a field in mathematics, the residue theorem, sometimes called Cauchy's residue theorem, is a powerful tool to evaluate line integrals of analytic functions over closed curves. It can often be used to compute real integrals as well. It generalizes the Cauchy integral theorem and Cauchy's integral formula. From a geometrical perspective, it is a special case of the generalized Stokes theorem. The statement is as follows. Suppose U is a simply connected open subset of the complex plane, and A1, and a finitely many points of U, and F is a function which is defined and holomorphic on U, A1, then if gamma is a closed rectifiable curve in U which does not meet any of the AC, if gamma is a positively oriented simple closed curve, I equals 1 if AC is in the interior of gamma, and 0 if not, so with the sum over those K for which AC is inside gamma. Here, res denotes the residue of F at AC, and I is the winding number of the curve gamma about the point AC. This winding number is an integer which intuitively measures how many times the curve gamma winds around the point AC. It is positive if gamma moves in a counterclockwise manner around AC, and 0 if gamma doesn't move around AC at all. The relationship of the residue theorem to Stokes' theorem is given by the Jordan curve theorem. The general plane curve gamma must first be reduced to a set of simple closed curves, gamma I, whose total is equivalent to gamma for integration purposes. This reduces the problem to finding the integral of f dz along a Jordan curve gamma I with interior V. The requirement that f be holomorphic on U0 equals U, AC is equivalent to the statement that the exterior derivative d equals 0 on U0. Thus, if two planar regions V and W of U enclose the same subset, AJ, of AC, the regions V, W and W, V lie entirely in U0, and hence is well defined and equal to 0. Consequently, the contour integral of f dz along gamma j equals V is equal to the sum of a set of integrals along paths lambda j, each enclosing an arbitrarily small region around a single aj, the residues of f at aj. Summing over gamma j, we recover the final expression of the contour integral in terms of the winding numbers I. In order to evaluate real integrals, the residue theorem is used in the following manner. The integrand is extended to the complex plane and its residues are computed, and a part of the real axis is extended to a closed curve by attaching a half circle in the upper or lower half plane, forming a semicircle. The integral over this curve can then be computed using the residue theorem. Often, the half-circle part of the integral will tend towards 0 as the radius of the half-circle grows, leaving only the real axis part of the integral, the one we were originally interested in. Example: the integral arises in probability theory when calculating the characteristic function of the Cauchy distribution. It resists the techniques of elementary calculus but can be evaluated by expressing it as a limit of contour integrals. Suppose t greater than 0 and define the contour C that goes along the real line from -a to A, and then counterclockwise along a semicircle centered at 0 from A to -A. Take A to be greater than 1, so that the imaginary unit I is enclosed within the curve. The contour integral is since It is an entire function. This function has singularities only where the denominator z2 plus 1 is 0. Since z2 plus 1 equals, that happens only where z equals I or z equals -I. Only one of those points is in the region bounded by this contour. Because f is the residue of f at z equals I as according to the residue theorem, then we have the contour C may be split into a straight part and a curved arc, so that and thus using some estimations, we have and note that, since t greater than 0 and for complex numbers in the upper H-plane the argument lies between 0 and pi. One can estimate therefore if t less than 0 then a similar argument with an arc C that winds around -I rather than I shows that, and finally we have example 2. The fact that has simple poles with residue 1 at each integer can be used to compute the sum Consider, for example, let be the rectangle that is the boundary of with positive orientation, with an integer n. By the residue formula, the left-hand side goes to 0 as since the integrand has order. On the other hand, thus, the residue it is. We conclude, the same trick can be used to establish we take with w a non-integer, and we shall show the above for w. The difficulty in this case is to show the vanishing of the contour integral at infinity. We have, since the integrand is an even function and so the contributions from the contour in the left half plane and the contour in the right cancel each other out. Thus, goes to 0 as. See the corresponding article in French Wikipedia for further examples.